Welcome to First Principles Daily, episode 34 for July 9th, 2026. Let's run the magic wand number and the idiot index on today's subject. A mile of subway can cost $2 billion in one city and a tenth that in another, even with similar rock and water tables, because the raw materials and boring hours explain almost none of the difference. In high-cost cities, a single mile of new subway routinely lands between $1 and $3 billion. Comparable tunnels elsewhere finish for $200 or $300 million. The difference is not geology or tunnel diameter. It sits in the layers of process, contract structure, and accumulated delay that sit on top of the physical work. The raw concrete, steel, and machine time required to bore and line a tunnel form only a modest slice of that final bill. That is why the gap itself is the clearest signal that the cost is not set by physics. Urban subway construction follows a pattern that has become self-reinforcing. A project begins with years of environmental review and public comment. It then moves into detailed design that must satisfy dozens of separate agencies. Utility companies own the rights to move their own pipes and cables. Every relocation therefore becomes a separate negotiation that can stretch for months while crews wait. Labor agreements often require specific crew sizes and overtime rules that were written for an earlier era of hand excavation rather than continuous tunnel boring. Procurement rules in many jurisdictions force the owner to award the lowest bid on a design that is already frozen. That leaves no room for the contractor to suggest cheaper methods once ground conditions are better understood. Stations add another multiplier. Instead of repeating a single platform layout, each new station is treated as a signature civic building with custom architecture, artwork requirements, and bespoke mechanical systems. Change orders accumulate because the original design cannot anticipate every utility conflict or groundwater surprise. Each change must be priced and approved through layers of oversight. Financing costs compound during the long schedule. Interest and escalation on a multi-year delay can equal another 20 or 30% of the original budget. In lower-cost cities, the same physical tunnel is delivered with shorter review cycles, standardized station modules, and contracts that give the builder more latitude to adjust methods in the field. The high-cost path feels normal only because every participant has adapted to it. No single actor set out to make the project expensive, yet the incentives align to keep the process fragmented and slow. One objection sometimes raised is that dense urban environments simply contain more conflicting infrastructure, so higher costs are inevitable. Yet the same cities that once built their original subway networks at far lower multiples of material cost now face the same geology and density. The difference lies in the added procedural steps rather than in the ground itself. Another common point is that safety and accessibility standards have risen, and those requirements do add concrete, steel, and systems. Even after accounting for wider platforms, additional emergency exits, and modern ventilation shafts, however, the documented cost spread between otherwise similar projects still exceeds what those upgrades alone would explain. That again points to the surrounding process layers. A rough magic wand estimate starts with the physical tunnel itself. A typical running tunnel for a modern subway is bored at roughly 6 meters in diameter. The concrete lining might total on the order of 4,000 to 6,000 cubic meters per mile. At commodity concrete prices, that volume represents perhaps $200,000 of material. Steel reinforcement adds another $100,000 or so. The tunnel boring machine itself, if purchased outright and amortized across many miles, contributes machine hour costs measured in the low millions rather than tens of millions when spread over a full project. Adding power, water, and spoil removal brings a first principles floor for the bored tunnel segment itself into the range of perhaps $5 to $8 million per mile. Stations and systems raise that floor, but even a fully outfitted station built from commodity concrete, steel, escalators, and track still sits well below $100 million when every element is priced at raw material plus standard fabrication rates. Compare that floor to observed project costs. In several documented high-cost corridors, the all-in figure reaches or exceeds $2 billion per mile. Dividing the finished price by the estimated material and machine floor produces an idiot index on the order of 200 or more. That ratio does not mean the concrete or steel is overpriced. It means the overwhelming majority of the expenditure occurs in activities that sit outside the physical act of excavation and lining. The largest visible slices are extended environmental and permitting timelines that keep capital tied up for years. They also include repeated redesign cycles driven by changing stakeholder demands. They include utility relocation programs that must be negotiated one owner at a time. They include risk premiums embedded in every subcontract because the schedule and scope remain uncertain. Each of those layers adds cost without adding concrete or steel. Because the ratio is so high, even modest compression of those non-physical steps would move the total price dramatically closer to the floor. A natural question is whether the station fit-out itself, rather than the tunnel, accounts for most of the gap, even granting that platforms, mezzanines, escalators, signaling, and fire life safety systems multiply the material quantity several times over. The arithmetic still leaves the bulk of observed spending in the same non-physical categories. The station concrete volume might reach perhaps 20,000 cubic meters instead of 5,000. Yet the same commodity pricing keeps that element in the low millions. The documented overruns continue to trace to sequential approvals, redesigns after bids are let, and carrying costs during multi-year delays rather than to any sudden jump in rebar tonnage or pump prices. A redesign would begin with the station itself. Instead of treating every station as a unique architectural commission, a repeatable module could be developed once and then replicated with only local adjustments for depth and entrance location. That single change removes repeated design fees, repeated regulatory reviews, and repeated custom fabrication of platform edges, stairs, and mechanical rooms. The next target would be utility coordination, a pre-agreed protocol that lets the tunnel contractor relocate minor utilities under standard rates, with major transmission lines pre-mapped and pre-funded by their owners, would collapse months of sequential negotiations into parallel work. Procurement rules could shift from lowest bid on a fixed design to best value contracts that reward schedule compression and documented cost reductions. That would align incentives so that the builder profits by finishing early rather than by extending change orders. Policy changes would also be required. Predictable eminent domain timelines and coordinated environmental review that runs in parallel with preliminary engineering would shorten the period during which carrying costs accumulate. None of these moves removes the need for safety standards or public input. They simply move those requirements earlier and make them apply to a standardized template rather than to each bespoke project. The genuinely hard constraints remain political. Neighborhoods that oppose new stations, labor agreements that resist changes to crew rules, and funding mechanisms that reward large one-off appropriations over steady multi-year programs all play a role. Those frictions are real, yet they are not laws of physics. They are arrangements that other jurisdictions have already altered enough to deliver tunnels at far lower multiples of the same material floor. One objection is that standardization would reduce the ability to respond to unique site conditions such as varying groundwater or archaeological finds. A modular approach can still incorporate adjustable parameters for depth, soil type, and entrance orientation, while freezing the interfaces that repeat. Platform edge height, escalator pit geometry, and ventilation shaft cross-sections are examples of those repeatable interfaces. Only the variable portions would trigger new reviews. Another concern is that shifting procurement toward best value would invite favoritism. Transparent scoring criteria tied to verified schedule and cost outcomes, published after each project, can limit that risk while still allowing the builder to propose method changes once the tunnel face is exposed. One principle is that when the largest cost items are measured in years of review and negotiation rather than in tons of concrete, the binding constraint is the number of sequential handoffs between separate organizations. Another is that standardization only reduces cost when it is applied to the interfaces that actually repeat, such as platform geometry and utility connection details, rather than to the parts of the project that truly differ by location. The question is which city or agency will first publish a single repeatable station module and then measure how many months and dollars disappear once that template is used on the second and third mile instead of the first. That's first principles daily for today. If this changed how you see what things cost, share it with someone who'd appreciate it and subscribe wherever you listen. I'm Patrick in Vancouver. One example or one opportunity every day. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. And before you go, this show is part of the Nerra Network, a family of daily podcasts on tech, science, and markets, each one a short, sharp briefing you can finish on the commute. If today earned its place in your feed, here's your next listen. Tesla Shorts Time, your daily deep dive into everything Tesla. Find every show free at nerranetwork.com. Live dashboards, TSLA, SpaceX launches, the investing scoreboard are all at nerranetwork.com/data. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own. I'm about to prove